Hello, good evening. Welcome at the evening session. Hello, thank you for joining me. Okay, if you have some question, maybe we can use like few minutes and you can ask me any question. If not, we can start chapter 2. We can start a new section. Okay. Yeah. Okay, I mean, you can ask me, okay, we do have a question. Oh, you can't hear me? I always use, ironically, I always ask you if you can hear me. Okay, Jack, please check because I can see that the other students can hear me. Okay, please check because I don't hear myself. I mean, I do, but not electronically. Okay, please check. You may possibly leave the session and come back. Yes, sometimes it works. Okay, but I'm assuming that rest of the students can hear me. Okay, that means let's start, and I hope Jack will fix his. Okay, good, great. Okay, that means what we will do tonight. We will start chapter 2, and you can see what section 2.1 is about the derivatives. That means I will finally introduce the main thing. I mean, one of the important thing in calculus, that is derivatives. You probably hear about this, and as I mentioned like yesterday, you probably had some of the students had calculus maybe many years ago, maybe you just remember, but you definitely heard about derivatives. That means let's actually see what it is. I will move to my other screen. That means let's start, okay? And I can tell you one thing. Always like the first sections of the new chapter is like more theoretical, okay? And then later on, of course, we will have lots of formulas, lots of shortcuts, and then we can speed up with our calculation. But always the introduction is like we would like you to understand the meaning of everything, what we will calculate later, of course, to have the proper definition, some other properties, theorems, okay? That means just to warn you. Okay, that means let's see, derivatives. What we will do, we will take the concept that we did in section 1.4, the tangent line, the slope of the tangent line, okay? Let's look at this. We probably remember this picture. That means we do have a curve and the pink line is a tangent line. And we did calculate the slope of the tangent line. We know that this is the limiting position of the slope of the secant line. Okay? That means we do have a blue line. I do have my pen, okay. We do have a blue line, which we know that is the secant line because we have point P and point Q, but the x coordinate of the Q, it's a little bit far away. That means we really have to x has to be extremely close to the point A, and then we will have 2 points close to each other, and then the blue line will be almost like the tangent line. That means that's the definition of the slope of the tangent. We creating a limit of something, of some scenario. That means first of all, we remember the slope of the line PQ, which is just f of x minus f of a, x minus a. Like really general saying f of b minus f of a, b minus a. Yeah, like just the rise over run. Okay, that's yeah, not a problem. And this one I can call, based on my picture, I can say the changes along the y, changes along the x, rise and run, delta y, delta x. Okay, but that's the slope of the secant line. That's secant line. Okay. And now this is the thing that we have to do. I just copy the picture from your textbook. That means they showing this way, but that's the same idea. We have to get closer and closer to the pink line. And this is the definition. Yeah? Slope of the tangent line is the limit of the slope of the secant line. Okay, just the old stuff, the recall from section 1.4. And then we can define, that's the first definition, I can define the slope of the tangent line. Okay? The tangent line to the curve f of x at the point A, f of A, is the line through the point P with the slope, okay? And this is the slope. We can see we do have a slope of the secant line and the limiting position. We know the notation. Limit as x is approaching A. The x coordinate of the point Q is getting really close to the point A. Okay? And this is still the slope. That means since x is almost A, we can see this is almost 0. Yeah? And this will be almost 0. Yeah? It's not 0, it will be tiny rise over run. And we remember the application, like in physics, the velocity, distance over the time. Tiny distance, tiny time. It will give me the instantaneous rate of change. Yeah? Okay, but that's the definition. But what we will do, we will, okay, I do have an exercise because I wanted, let me come back, I wanted to twist this definition, to change a little bit, but let's use this definition to actually solve this question, which we actually did this question in section 1.4. Do you remember? But we use, I used the calculator and I was like choosing the x coordinates of the point Q to be really close to point 1, like 1.9, 1.5, 1.1, 1.01, and even closer. And also on the other side, 0.5, 0.89999, and so on. But we will, of course, we will not do this because we know how to compute the limit. We can use our definition. That means we will use this definition because finding the equation of the tangent line to the parabola x squared at the point 1, 1, we can use the point slope form. Okay, and we do have a point 1, 1, but we need slope. Okay, m is slope, and that's how we will calculate that slope. Okay, f of x minus f of a, x minus 1, I mean that's f of 1, x minus 1, and x is approaching 1. And what I can do, instead of f of x, I can put x squared. Okay, that means, can you see now? It's the whole chapter 1, section 1.6. Yeah, the calculating of limits. Probably you can tell me. That means let's this to be the first question tonight. What is this limit? Do you think you can solve it for me? Because now it's just, yeah, now we do have a really nice introduction, really nice definition, theoretical part, but now it's the calculation. That means, what is this limit? Who can tell me? It's 0 over 0, excellent. This means that we do have a common factor, function, the upper function and the lower function. I mean the bottom and the top of this fraction. And yeah, I think it is 2. We can factor out, that's my 0. 0 is gone, 1 plus 1 is 2. Yes, thank you. Okay. But we can see we did. And if you remember section 1.4, we did, the approximation was also 2. Yeah? But now we know yeah? the technique. We are more mature. Okay, and then I'm just repeating the point slope form, substituting 1, substitute 1, 1, and 2, and just distributing 2x minus 2 and plus 1 will give me, too fast, will give me 2x minus 1. That means this is the equation of the tangent line, but of course the slope, this is important. Okay, let's keep moving. Okay, one thing that I have to like mention, that because we're focusing on the slope of the tangent, but we have to know that when we will be asked to find the slope of the curve, it's exactly the same thing. Because we may think, oh, how can I find the slope of the curve? Because curve is a curve. But actually, let's look at this picture below. Like if we do have a curve, yeah, and I will ask you, oh, let's find the slope of that curve. How we should understand this question? That we have to find the slope of the tangent line to that curve at this point. Okay, that's the same thing. Because what's happened, when we zoom in, when we go really, really close, yeah, when I will draw a tangent, the tangent will be almost like at the point of the tangency point, the point when the tangent line is tangent to the curve, the line and the curve, they look the same, almost the same. You may notice the scale. Yeah, I was like zooming from 0.9 to 1.1. It's almost the curve. You can, yeah, we can like imagine, like really curvy, like we can imagine some curve, and when it looks like, yeah, looks like a curve, but when I focus on one point, like let's say here, and if I will zoom in, if I will go really, really, really close, yeah, it will be like line, yeah, almost like a line. Yeah, that's also the idea of calculus. If we really understand this, that's good. Because we're getting really, really close because calculus, ironically, or maybe not ironically, but calculus deals with the tiny like numbers, amounts, and also huge. Okay, that means you can even imagine like now, of course, now now I'm in the office, I'm in the room, but when we go outside, and you can imagine like yourself being outside, and maybe even like taking off, being on the plane. Yeah, that's we going up, but let's imagine that we will like take some space shot, and then we can see the Earth like a sphere. Okay, that's the same. When I am here on the ground, I see flat. Yeah, I see everything, it's like flat. But when I go up, then I see the air as that's the same, yeah, the same idea. Everything is relative. Yeah, but that's calculus. That we can think that this point, the point of the tangency, will give me the straight line. That means slope of the tangent is the same like the slope of the curve. Okay, but for now, we focus on the tiny amounts. We will take off later on. Okay, that means what we can do now. Let's look at this. Okay, I will change the definition a little bit. That's the same thing. Blue line is the secant, pink is the tangent, and we know this. But what I will do, instead of like the point Q, I will define a little bit different, okay? That means I will still have my point A and f of A, because that's the important point. We focus on that point. Point of the tangency, we want the slope of the curve at that point. But the distance that I am like finding my Q, I will call this distance H, okay? That means the distance between point P and point Q along the x-axis. That means if this is A, this distance is H. This is of course A, the distance from, yeah. That means how can I name X in terms of A and H? Like this distance is A, this distance is H. That means this point will be defined as a plus H, correct? Yeah. Okay, that means I will change x for a plus h because I'm moving h units away. And this will be f of a plus h. That means a is my point of the tangency and I'm moving away. And, oh, we have somebody, I think Eric, you should mute your microphone. Or maybe I can mute. Okay, I did mute everyone. Okay, that means we can see. And now, of course, I want point Q to be extremely close. That means the quantity H will be almost zero for my tangent line. Okay, that's we have to move away. We have to find a point close to the P, but extremely close. Okay, but let's rewrite. That means, as I said, the X is defined as a plus H. This will stay the same, but now the quantity X minus A, because we can see X is defined as a plus H minus that A will give me just H. And makes sense. The H now is the run. How far? Not far, of course, we're extremely close, but how far I'm running away. H units. Okay? That means what we will do, we will actually use this definition. Okay? This is still the slope because f of a plus h minus f of a represents the rise and h represents the run. Okay? It's still the slope of the secant line. When I add the limit, okay, which means when I will say that h is approaching zero, then it's the slope of the tangent line. Yeah, I'm just changing this because I can tell you it will be easier for the calculation that we have to perform. Okay, that's when we do have this picture. And now I can show you this definition again as a second definition, but with the h, okay, the h notation. That means it's the same thing. We know f of x minus f of a, x minus a, rise over run, but I use the h notation. Because what's happened, x and f of x was the coordinates of the point Q, but we also have a function which is called f of x. And sometimes we can get a little bit confused with the calculation. Okay, that's just and now you can see like we do not have in this definition limit as h approaches zero, f of a plus h minus f of a over h. We don't have x. We will reserve x for the function f of x. That means this is important definition. Okay, everybody has to know this definition. Okay, that's me. Yeah. This is slope of the tangent line, okay? Defined this way. And what we can do, we can take another function and try to find the same thing like we did for parabola. Find the equation of the tangent line to the function 3 over x at the point 3, 1. Okay, that's mean, let's see. That's mean what we have to do, we have point, we have to find the slope first, okay? Okay, I didn't want to show you the picture first, but it's okay. We can see function 3 over x looks almost the same like 1 over x. A little bit like higher values because we're multiplying by 3. That means the blue curve, it's our function. And actually this pink line, it's a tangent line. And we have, yeah, weird form. We have the standard form. We don't have the slope intercept form. But can you tell me what's the slope of this line? Because that's what we're looking for, and we will compute. Can you give me the form mx plus b? Do you know how to rewrite this? We have to subtract x and add 6 to both sides and divide everything by 3. That means it will be negative 1/3 x plus 6 over 3 plus 2. Thank you, Dave. I was trying to. Okay, that means the slope of this line is negative 1/3. And we do have a function, we know the definition, we will try to get this number. because this is one of the main exercise for this section. Okay, that means this is slope, okay, of the tangent, of course. Limit as h goes to 0, f of a plus h, but my point A, my point of the tangency, A and f of A, it's 3, 1. Okay. That means now we do have to evaluate our function for 3 plus h. My function is 3 over x. Okay, f of x is 3 over x. If I will ask you to evaluate for a, you will just replace x with a. If I will ask you to evaluate for t, we will say 3 over t. If I'm asking you to evaluate for, I don't know, the triangle delta, we will replace x with this. But when we are asked to evaluate for 3 plus h, instead of x, we will put 3 plus h. Okay, that means evaluation, it's quite trivial, but sometimes I know we will like ask where the formula come from. Okay, that means f of 3 plus h is 3 over 3 plus h. And f of 3, actually I should ask you evaluate for 3. We have to substitute instead of x 3 over 3 is 1, but we actually have the point given. Yeah. Okay, that means this is the evaluation. We have to know how to evaluate easy. Every single x in the formula replace with the quantity given in the parentheses. Okay, and now we have another limit. That means we will need, again, skills from section 1.6. When we substitute h0, I will have 0 over 0, okay? And this is the type that we still have to find this common 0 and cancel out, but first of all, we have to rewrite. That means what we can do, since we still like lots of fraction, I can multiply each term, the first one, this one, and the denominator by 3 plus h, because 3 plus h is a tiny denominator on the fraction from the top. And when I multiply the big fraction on the top with 3 plus h will be cancelled out. When I multiply 1 by 3 plus h, it will be 3 plus h. And h times 3 plus h. Okay, makes sense? And you can see we did have negative. I keep that negative. And I will not distribute the denominator because this is my problem. I will distribute negative, please remember, because that's common mistake. And now a little bit of arithmetic. Now can you see the common 0? H and h gone. Yeah, I'm just evaluating the limit. And now I can easily substitute for h0, and actually, yeah, this is 0 now, fine, no problem. And this is slope, negative 1/3. Yeah, that's what we got. Yeah. That means the whole process is extremely important. Maybe after the session or maybe tomorrow during the lunchtime, you can try maybe to look at this question again. Don't look at my solution and try to do it again. Okay? I mean, we can theoretically take any function and try to find the slope of the tangent line at the given point. Okay? We will always use this definition. That's the definition. Okay, I will erase the a's. Okay. And then point slope, that's easy. So you wouldn't cancel 3 plus Eric, you asking for this part? Oh, no, we have subtraction. When the number is involved in this addition or subtraction, we can't cancel out, like 1 plus 2 over 2. Over 2, I was thinking. Do you think 1 plus 2 over 2, I don't even want to write this down. Do you think this is 1? We can't cancel out if we have addition and we have subtraction. Like, I mean addition and subtraction. That means no. As soon as we have product, yeah, factored form, product form, then we can cancel out, okay? I know it's looks like, yeah. Okay. Okay, but yes, good, yeah, good question. Okay, now let's quickly look at the velocity, but we don't even have to say much because we know the average velocity, average speed is the distance or displacement over the time. And this is just, I just type it for you again with the h. Yeah? Instead of like f of b minus f of a, b minus a, we do have this h notation. And we remember the average velocity is exactly the same calculation like slope of the secant. Instantaneous velocity, like the velocity at that point, at that instant, is exactly the same like exercise like a slope of the tangent. Okay, that means the instantaneous velocity, it will be actually the same limit. Okay, that means this limit represents the instantaneous rate of change. How function f, how the curve f is behaving, yeah, at that instant. Of course, I'm thinking about the slope of the curve or slope of the tangent, or overall instantaneous rate of change. Okay, that's the information. And now, finally, okay, finally, that means what I would like to say, that this type of limit, as I said, in general, if we would like to find out how things are changing, okay, like everything, I focus only on like slope of the tangent and the instantaneous velocity, but we may have lots of different, like how, I don't know, how some inflation or some interest rates or some investments or other like different, like in engineering maybe, or in science, like different quantities, some growing population, how things are changing at that instant. We will always use this limit. Okay, and how we name this limit, since it's so like often so widely used, we do have a special name and special notation. And what is the special name? You can type it. I will be happy if you will say for the first time in our spring, yes, the special name of this limit is derivative. But at the moment is the derivative of the function f of x at the given point, at a. Okay, that means that's, yeah, we will change a little bit. Okay, Noah has a question. Yes, h is the distance, like how far we're going away from x. And yes, theoretically, I mean from a, I should say a. Yeah, that's mean, yeah, no, it's, I mean, it's involved. Okay, let's say, that means this is a, and then my point q, that means I can say this way, it will be a plus h. That means h is actually, I'm of course trying to, this is h. I should draw bigger, but I'm thinking like small. That means h is just the distance that we're going away from the point A, okay? And yeah, q will have a plus h as an x coordinate, but it's not really just the coordinate, that just is, it's part of the coordinate. Okay, that means one more time, finally, this special name of this limit is the derivative. That means this is the derivative. And we also have a special notation, yeah, like how to indicate this. We will take a function, okay, and I will say it's like still everything is evaluated at the point of the tangency at A, or the point of that instant, at that moment. And I want to make a difference. That means this is the notation. We will say like f prime. Okay, that means this means the derivative. F prime of A, and that's the definition, it's the derivative of the function f of x at A. Okay, and so far we know that this defines the slope of the tangent or the instantaneous velocity. Okay, because we will have different applications, but for now, yeah, let's focus on the beginning. Okay. Okay. This is the nice slide. And this is, you can see, this is the old, but as I said, the H notation is a little bit better. That means the derivative of the function f at the number a, yeah, denoted by f prime at a, is defined as a limit as h goes to 0 of the ratio, the difference quotient, f of a plus h minus f of a over h. And we know what this means. Okay, that means this is the derivative. Okay. We can find, okay, that's, we can try to find the derivative of the function. Actually, let's skip this one. That's too long. You can look at the solution later. You can check it. This is solved for you. Oh, let's find this one. This one I didn't type. Oh, great. Find the derivative of the following function, which is square root of x at the point 1, 1. Okay, that's, we have to find the derivative. We know what the derivative means. Derivative means the slope of the tangent line at that point. Yeah? That's also really, really helpful, because later we will like focus on derivatives, and we kind of like forgot what's really this is. That means, please remember, slope of the tangent. And I can even draw this situation. That's square root of x. The point 1, 1 probably is 1, 1. It's somewhere here. And the tangent line looks like that. Okay, that means we will not look at mx plus b. I don't know. But the derivative, okay, is that m value. Okay, of course, this is tangent line. Okay, that means, please remember, derivative, it's still the slope of the tangent. Okay, that means let's find it out. Let's calculate. Derivative at the point 1, it will be the limit as h goes to 0, f of, I can write a plus h minus f of a over h. Okay, let's evaluate. My a, of course, value is 1. F of 1 plus h minus f of 1 over h. Limit as h goes to 0. Okay, that means now I have to evaluate the function for 1 plus h. Square root of x will be replaced with 1 plus h, and square root of 1. Okay, maybe I can save room. Oh, actually, I don't even have to. And we also remember how to evaluate this limit. This is 0 over 0. Let me put 1 because it looks funny and I will not. Okay, that's when we do have, when I substitute h0, we have 0 over 0. And do you remember what we have to do if we see the square root expression? How we can rewrite, like how can we change? We will multiply by conjugate, yes? Thank you, Chuck. That's square root of this plus 1. Square root of this plus 1. Excellent. Okay, and limit as h goes to 0. And I will keep that h. I will not distribute this part, but I will distribute the conjugate expression. That means I will square the first quantity, I will square the second, and minus. Yeah? A plus b times a minus b is equal to a squared minus b squared. And we can cancel out. And you probably see limit as h goes to 0. And then we have h, and 1 plus h plus 1. And that's my 0. That's my problem, gone. And h is 0, square root of 1, 1 plus 1, 2. Okay, the slope is 1/2, and looks like 1/2 even with my graph. let's put x and y. Okay, that means again, this is also a good function. If I will be you, I will solve it again. Okay, it's good exercise. You see, and always put the limits, always. Or you can maybe pick one function and put on the discussion board. Yeah, because I really would like everyone to show me that you can follow this definition. Okay, let's keep moving because we can practice later, but I would like to say, we will skip this one because that's the same process. This one is even more crazy. Okay, I would like to do this exercise. That means actually one thing we can possibly do. Because what we did, I would like to, we definitely know the definition. Okay, we know the definition, and then we did evaluate, based on the definition, we evaluate the derivative for the given function. Okay. For example, this function, that's maybe, oh, maybe this one. We will not compute this, but let's just start. That means there are at a. Derivative at a, because we have to find the derivative, it will be limit as h goes to 0, okay? And then f of 3 plus h, you see I took that 3, minus f of 3, and then h. And let's just evaluate for the given function. It means I will have h, and how can I evaluate f of 3? Let's start with this one. Instead of x, okay, I will put 3. And 3 plus h, I will put 3 plus h, 3 plus h. Okay, that's we can see. This one is, yeah, we did evaluate for that function at the point 3. Because now what is my exercise? I would like you to see a limit, and I will tell you that this limit represents the derivative of some function at certain point. And you have to identify what is the function. Okay, this one maybe is a little bit crazy, but it's still, we can kind of see that this is my x. Yeah, that means x minus 1, x minus 2, and this was x minus 1, x minus 2. That means that's the function, and the point was 3. Okay, when we will check, for example, this one. That means, what do you think? Do you think you can see, because each limit, again, I will just repeat, represents the derivative of some function f at the some number a. And we have to state what is the function. Do you think you can, based on this, you can see what is the function? Or not really? Looks like because it's, I can reverse everything. X minus 1 over x. Oh, y over x. I can say, I can definitely see a plus h. Yes, a plus h to the power of 10 minus, let's say this way. Yeah, that means we know a. What is a value? Can you tell me the a value from this limit? Matching a is definitely 1. And what do you think? What is function? Function is simply just x, yeah, x to the power of 10. Okay, x to the power of 10. Because instead of x, I did put a plus h, and to the power of 10. Yeah, that's, let's look at this one. 1 over 2 plus h minus 1 over 2. Yeah, that means this, it's 1 over x. Yes, that means because that's extremely important skill. Yeah, looks like 1 over a plus h minus 1 over a and then h. That means a is definitely 2 and function is just, oh, I should maybe keep the 1 over x. And instead of x, we put a plus h. Okay, and let's do one more. What do you think? The 4th root of 16 plus h. 4th root of a plus h, and I believe this is 4th root of a. That means, what is a value? Can you tell me a? The 4th root, the 4th root. Yeah, no, it's okay. That's how we actually write on the, yeah. What is the a value? The a, it's 2 or 16? Yes, I think it's 16, because 4th root of 16 will give me 2. 2 is the value. Yeah, but the x, I mean the resulting, the corresponding value, the y value for x equals to 16. And then function is, of course, we just got, yes, 4th root of x. Okay. Okay, but let's, before I have more, but you can check, practice with Kasia problems, and I think I finished this slide. Okay, I have, yeah, that means I will leave this one, I will leave this one, and oh, I have a lot. Okay, and I will skip this question. Now let's do this. Let's solve this question as a last question in this section, and then we will start 2.2. Okay, we have 20 minutes. I think we can manage, because the 2.1 was important. You know the definition. Okay, let's see if we understand. Find the equation of the tangent line to the graph g of x at 5. If, and we have some given numbers, g at 5 is -3, g prime at 5, it's 4. Okay, that means we have to find the equation of the tangent line. We can use point slope. Okay. To the function g. That means, what is the x value? Who can tell me the x value? And then you have to tell me y, and you have to tell me this. The x value in this case, because we're looking, okay, it's 5. Thank you. That means, what is the corresponding value for 5? At 5, it's -3. Really good. And who can tell me what is the slope? It's, yes, okay, because this, yeah, this is telling me derivative means the slope of tangent line, of course, at the given point, and this is 5. Okay, that means I was just testing that 4, and you can distribute, and we can get the tangent line, but that's okay, that's important. Okay, I will actually, what I will do, I will stop sharing with you for a second, and I will share this, okay? Okay, that's, we know the derivative at one point. And what is in section 2.2? In section 2.2, we will talk about the derivative as a new function. Okay, so let's see what we will do. We know this definition. This is derivative at the given point, always the given point. We can always think like a point of the tangency, yeah? The given point A. But now I will let this point, the point of the tangency, A, f of A, I will let this point to change, to vary, okay? Which means I will simply replace this point with x. This will be, actually I can write like that. Okay, I will simply replace this with x. I will like, instead of like, because we can say, okay, we have a tangent at the point A, f of A. But then I can say, I don't have to have the exact value. I can say, oh, let's the tangent to be, I mean, let's the point of the tangency be like x, and x could be any number, 1, 2, 3, 4, 5. We will have like just different value. That means that's what I will do. Instead of like having a and f of a, I will say x and f of x, because this is point on the curve. That means I can name it x, x, x. That means I will just change a for x. Okay. And now, when you will see f prime of x, the final answer will be not in terms of the given value a. The final answer, if we will evaluate this limit, it will be in terms of x. That's the reason that we will call that this is a new formula, new function. Okay? That means, because previously we did compute the derivative, which was the slope of the tangent, but we did have a finite number, like we did the square root of x at the point 1, and we've got 1/2. Yeah, 1/2. But now computing, but this was exactly at the given point. Now my final answer will be like in terms of x, which we can even do the same exercise. Not substituting a, we will substitute x. Okay, that means I have a few notes, okay? Because the derivative as a new function, we can say it's called derivative because it's derived from a function, and still geometrically it will still can be considered as a slope of the tangent line. I mean, it is defined as a slope of the tangent line, even if we will have tangent line at x, and now we can pick any value for x. Okay, yeah, it's derived. And when we have a function and we will compute the derivative as a new function, domain could be, the domain of the derivative could change a little bit. Sometimes we eliminate some numbers, okay, doing this limit process. Yeah, but that's it, just a few notes. But let's find the derivative of some function as a new function. Oh, for example, x. If f of x is equal to x, find the formula for f prime of x. And we can definitely follow the limit notation, the limit definition. But what do you think? Because I think you can answer this question. What is the derivative? What is the derivative of the function x? The line y equals to x, what will be the derivative? Oh, and one thing, when we have the notation f prime, we can also have the notation, is the same thing like y prime. Yeah, because when I'm not using my f of x, I am using my y label, I can say y prime, that's the same thing. That's mean, what do you think? What is the derivative of the function x? You think you can answer this question? What is the derivative? Okay, Justin is saying 1. Does everybody agree with this? Okay, I mean, if you don't feel like saying something, and Dave is saying 0. Okay, that's me now. I don't know. Okay, maybe Justin, maybe you can type, maybe you can answer, why did you say 1? It's a little bit, yeah? I mean, it's simple question where because y equals to x, but that's the function, y equals to x. You have to say a little bit more, then I will know that maybe you're thinking correctly. Yes, that's what I was waiting for. Exactly. When we have a linear function, they don't change. Yes, they don't they climb or they decline with the same slope. Because derivative is the slope of the tangent line. But when we have a line, tangent line to the line, is the same line. Yes, that's what is, yeah. We just need the slope, okay? And slope, it's 1, which means y prime, I can use that notation, is 1. Yeah? And when I will give you the function 2x, what's the derivative of 2x? 2, thank you. If I will give you 1/2 x, what's the derivative of 1/2 x? Of course, 1/2. And maybe this one looks a little bit x over 3. What will be the derivative of x over 3? Of course, 1/3. I just wrote differently. Oh, yes. That means, please remember, when we have a linear function, it's extremely easy. We don't have to do anything. If I will give you different function, like even x squared, then we don't know. Okay, then we have to follow the formula, and yeah, but linear function, perfect. What about the derivative of the constant function? Let's say 5. What will be the derivative of 5? 5 is just the constant function. 0. Because what's the slope of the horizontal lines? Yes, no, I mean, oh, no, Chuck, we do have a slope. Slope is 0 for the vertical lines. Okay, that's another good, actually, question. What will be the slope? Let's say 3, x equals to 3. What's the slope of this line? What's the slope of the vertical line? Undefined. That means, look how lots of, really good. That means what I can say, vertical lines, they don't have slope, right? I mean, I wanted to say my calculus statement. We know that vertical lines has no slope, then what this means? No derivatives. Yeah, really important thing also. Yeah, it's also, of course, it's not a function. Yeah, but even if we don't have a function, like we have a curve, we can still try to find the slope. Yeah, but yeah, you can say, we can also say this way, but I will prefer to focus on the slope. Yeah, it doesn't matter if it's not a function, it's still a line. Yeah, and any line theoretically has a slope, but no vertical. No slope, no derivatives. Okay, but what I did, yeah, that's, yeah, okay, Dave. Okay, but what I did, I followed the formula, f of x plus h minus f of x over h, and then I did evaluate for the function. That means function is just x. That means I did put x plus h minus x. I cancel out x's, h over h, 1. But you can see we don't even have to do it because you gave me the answer. The derivative is 1 because the slope is 1. Really good thinking. Okay, that's me. Now let's do x squared. Okay, let's find the formula for the derivative f prime of x for the function x squared. Okay, this one we don't know because function x squared, of course, is the parabola. Okay, and it's changing. Okay, it is like like when I pick my x value here, then that's the slope. When I pick the x value here, this is the slope. Slope. Yeah, because derivative means the slope. That means I have to find the general formula that will represent the slope of the tangent at any point. Okay? Whatever point I will pick. Okay, we will start with the definition. F of x plus h minus f of x over h. H goes to 0. Instead of x, I will substitute x plus h squared and x squared. Yeah, we can see we don't have a now, x. I will expand x plus h squared. We know the formula. I saw the discussion. Somebody asked for the formulas, but we can just FOIL x plus h times x plus h. And then I see h and h as a common factor. I factor out h, and h is my problem. Yeah, h is the 0, and 0 is gone. And now we can substitute instead of h0, the final answer is 2x. Okay, that means derivative of x squared. Oh, I'm pressing my buttons on the laptop. The derivative of x squared is 2x. Okay, and again, I will really ask you to even like write down this process. Okay, because it's really important. We will definitely, yes, I will definitely ask you some question on the quiz, on the test, on the exam, like how to go through the limit definition and get the derivative of the function. Because later, as I said in this chapter, we will have lots of shortcuts. I'm sure we have students in the classroom that if I will ask you what's the derivative of x squared, you will give me 2x. But this is the way, yeah, to get through the limit. We know what this limit means. Okay, that's what I have in this section. I have because now we can take any function and find the derivative. Okay, that means I think I have x cubed, but you can check the solution. The same thing. I have 1 over x. You can try to look at this solution later. And we will not do this one. That's too crazy. I mean, you can practice. Because I would like to say few things before I finish. For all of the practice that I skipped, you can check, yes, my video, the practicing video. I have square root of x. That's the derivative. Oh, that's too crazy. Okay, I wanted to show you this. That means what we have, the notation. Okay, that means we know that we will call f prime or y prime. We also have a notation that looks like this, dy dx. It has nothing to do with the fraction, it's just the notation. That means we can read like derivative of the function y with respect to x. Okay, that's when we're differentiating with respect to x. Okay, or we can say derivative of the function f of x with respect to x. Yeah, but dy dx, we will use this a lot. This one is just for some of the textbook are just using this this notation. And just in case, if we have to evaluate the derivative at the given point, yeah, we will put f prime of a. But when we using dy dx notation, we can just indicate like underneath that x is a. Okay, that means just this. Okay, the notation. And because now you actually gave me the really nice example, the vertical line. The vertical line actually doesn't have derivative. No slope, no derivatives. That means what we can say, if the function has the derivative, we will call that the function is differentiable at the point A.